In this video I'm going to be talking about the Jacobi method for solving a system of linear equation. Now the Jacobi method is a so-called indirect method. Okay, so that indirect method means we use several applications of it to give us a solution to our problem. And our problem is this. So we have a linear system. Okay, so A is a coefficient matrix, X is a vector of unknown values, and B is a constant vector. Okay, what I want to do first is I want to rewrite, pick a colour, I want to rewrite A as a sum of three matrices L plus D plus U. Okay, and L, this is going to be a lower triangular matrix, D is going to be a diagonal matrix, and U is an upper triangular matrix. Okay, so if we think of an example, let's just look at a 3x3 example. I'm going to use numbers. 8, 9. Okay, so let's say that was our A. Okay, in this case, L, the lower triangular elements of L would be 4, 7, and 8, because that's the lower triangular elements of A, and all other elements would be 0. So that would be L. D would be only those on the main diagonal, would be non-zero, and all other elements would be 0. And if we had U, so all of our main diagonal and lower triangular elements would be 0, and we just got the non-zero elements on the upper triangular region. Okay, so that's what we mean by L, D and U. Notice L and U are different from LU factorizations, so try not to get those confused. Okay, so recall that we're trying to solve this system. AX equals B, and we can rewrite A as the sum of L, D and U. I tend to use L, D and U in that order just to, just for clarity's sake. Okay, and what I'm going to do now is I'm just going to separate L and U from D. Okay, so we've got L plus U times the vector X plus D times the vector X equals B. So I haven't done anything strange, I haven't done anything strange here. It's just multiplied out, and I've just grouped those together. Okay, so if I subtract this first term from both sides, I get B minus L plus UX, and then if I pre-multiply both sides by the diagonal matrix, or the inverse of the diagonal matrix D, we get this. Okay, so this is vector and matrix form. Well, this is an implicit equation, so we have our X vector on the left and we also have our X vector on the right, but what I'm going to do is I'm just going to put a k plus 1 in a bracket in superscript. Okay, so what I'm going to do is we're going to turn this into an iterative scheme. So on the x on the left I've got k plus 1 in bracket, and the x on the right I've just got k in bracket. So k is our guess, or our guess is our estimate of a solution. So if we have some estimate of a solution xk, okay, so that's our say our current estimate. So that's our current estimate of x, and this one on the right is our improved estimate. So what we're saying is, if we calculate this equation here, so that's our improved estimate of x. So if we calculate this equation here, we're going to improve our value of x. So we start with some guess of our solution, so that will be our vector x, and we calculate this and we improve. Okay, what we can do is we can actually write this out for each element of x. So for the ith element of x, okay, we can write this out. The inverse of the diagonal matrix is just 1 over the main diagonal element, and because the values on the main diagonal of D was just values of AII, so we've got 1 over that, times BI minus, and here we got a sum Okay, so and L plus U. So whenever L is non-zero, U is going to be 0, and whenever U is 0, L is also going to be non-zero. So it's just going to be all elements. J equals 1, but J can't be equal to I, so we're not including I in our summation. Okay, and N is a number of equations in our system. Okay, that's multiplied by Aij, xj of the current estimate. Okay, so this thing I'm boxing here, this is what's known as the Jacobi method for solving linear systems. Okay, so let's have a look at an example. So I'm going to pick an example, just a 3x3 example, so we're not doing too much work. This example isn't in your notes at all, so it is worth noting down if you're following along with this video. Okay, so I'm going to suggest a 3x3 system with the coefficient matrix 2, 1, 1, minus 1, 3, 2, 1, minus 2, 4. Okay, so then we've got a vector of unknowns, and we've got a right hand side vector, which is going to be 4, 3, 9. Like I said, this is a new example. Okay, so if we apply the Jacobi method for this, the equation for our first value is going to be 1 over A11, so that's going to be 1 over 2, multiplied by B1, which is 4, minus 1 times x2, so that's going to be the kth value of x2, or our current iteration, sorry, and 1 times x3, or minus 1 times x3 of the current iteration. Right. The second value, or x2, okay, will be 1 over A22, so it's 1 over 3, B2, which is 3, minus, so that's going to be a plus, minus x1. Okay, so now all the ones on the right hand side are the current estimates, and minus 2, so I've missed out the 3 because that summation we don't include the when j is equal to I, so we've got minus 2 x3. And finally, the improved estimate for x3 is 1 over A33, which is 4, B3, which is 9, minus x1, or our current estimate of x1, minus, that'll be plus 2 times our current estimate of x2. Okay, so these are the Jacobi iterations for this system. Okay, so we need a starting point. So what I'm going to use is starting point or initial guess values. I'm going to choose all the zeros. It doesn't matter what values you choose to start with. If the Jacobi method does converge, it will converge to the correct solution. There are some times when the Jacobi method doesn't converge, and we'll come on to that in another video. So for this example, I'm just going to use the starting values of all the zeros. Okay, so for our first iteration, k equals 1, so x1 is going to be equal to 1/2 4 minus x2, which is 0, minus x3, which is 0. To start with, remember all of our values are 0, so that's going to be equal to 2. For our x2, we've got 1/3 of 3 plus x1 minus 2 x3, so that's going to be 1. And for our x3 value, our first estimate is going to be 1/4 9 minus 1 plus, sorry, 9 minus 0 plus 2 times 0, which could be 9 over 4, which is 2.25. Okay, so that's our first estimate. Well, sorry, our first iteration. So that is an estimate of the solution. It's not going to be particularly good because we've only done one iteration. So what we do is we keep iterating. So if I do the whole thing again, so this time I'm on my second iteration. So this time we got 1/2 4 minus x2, but x2 is now 1. So and then minus x3, which is now 2.25. And that equals to 0.375. Okay, x2 is 1/3 3 plus x1, so x1 was equal to 2, minus 2 lots of x3, and x3 is 2.25, and that equals 0.16 recurring, so I just put recurring symbol. And finally x3 on our second iteration is 1/4 9 minus x1, which was 2, plus 2 lots of x2, which is 1, and that's 2.25 again. Okay, so you can see these values are different, so we went from 2 to 0.365, 1 to 0.16 recurrent. Okay, so generally speaking, the more you iterate, the more we go through this process, the closer these estimates of our solution will get to the actual solution. But of course we can't go forever. Okay, so we need to know when to stop. So this is the idea of what we call the residual. So the residual, okay, that's defined as some vector r. So the residual is a vector is equal to our constant vector minus a times our vector x. So remember, we're solving ax equals b. So the residual is some error. So if we had our value of x, okay, let's say that's our kth estimate of x. If that was exactly equal to x, our error will be 0. Okay, so what we do is we iterate until the norm of our residual is less than a given tolerance. So that tolerance is just some small number. So we've used that before in this course. So usually 10 to the minus 4, 10 to the minus 6, etc. Okay, so for our second iteration, if we calculate the residual, so the b vector was 4, 3, 9. You need to go back in this video, just rewind to remind us what the b vector was. A was a matrix 2, 1, 1, minus 1, 3, 2, 1, minus 2, 4, and that's multiplied by our current estimate of the solution, which was, after 2 iterations, we had 0.375, 0.16 recurring, and it was 2.25. Okay, if you calculate that, you get 0.83 recurring, minus 1.625, and minus 0.04, 7, etc. This is just 4 decimal places. So if we were to calculate the normal of that residual, at the moment that would come out as 1.8267. Okay, so you can see that's much bigger than if we were to say, for example, toll was equal to 10 to the minus 4. That would be much bigger than toll. So we need to continue our iterations of the Jacobi method. If we do continue, hopefully the estimate will converge and the norm of the residual will become less than whatever tolerance we want, and then we say, okay, that's our solution for our linear system. Not all systems will converge for the Jacobi method, but as I said, that's a subject for another video.